So my name is Paul. I'm a grad student working at LP. And today we're going to talk about reasoning. We've looked at representation, we've looked at alignment. Reasoning is the next sub-challenge, as you all have seen. So what is reasoning? Reasoning is all about combining knowledge, usually through multiple steps that exploits multimodal alignment and problem structure. So you see local representations, right? You take two elements for both modalities, you can learn a representation between them. We've also seen aligned representations. If we take multiple elements from multiple modalities, how do you learn representations that exploit alignment across all elements? So now we have all these individual pieces of information. Reasoning is about taking all this and composing them to make a final prediction. It's all about combining and composing knowledge. So why is reasoning difficult? So I'm going to give a very, very simple example. You have an image and a text caption and trying to match whether they're the same or different. So you can train all the big models you want, like Wilbert, big language pre-trained models, image pre-trained models. And they do really well for this case, right? You see some plants surrounding a light bulb. That's something you see every day. You've probably seen something similar in a training data set. You can match it very well with the image. You just change the caption a little bit, and you change the image a little bit, you get a light bulb surrounding some plants, and you get a corresponding image. Almost all language models and all pre-trained models fail on this task. Right, so whether you take Clip, Wilbert, all the big large-scale pre-trained models, they all perform only as good as random chance on these other examples. And this has been known for a long time, like even before this era of big pre-training, this is known as the compositional generalization problem. How do I generalize to novel combinations of my data that I haven't seen during training? I've seen plants and a light bulb, I've seen the first order, how do I generalize the other order? So this is really, really difficult because again, you don't see these cases. This is like you can call it edge case, you can call it adversarial example, you can call it out of distribution, but regardless, we want our models to be robust to all of these cases. And people have slowly started to realize that just pre-training on more data is not going to get us to compositional generalization. This is a hot debate. Some people think it can, some people think it can't. I personally have the view that you need some domain knowledge, you need some structure in your models, and that is where reasoning comes in, right? What is the right form of domain knowledge to ensure that we get closer to compositional generalization? So look deeper, how can we actually solve these cases? Well, in order to correctly match a light bulb surrounding some plants, you need to understand the structure of the problem, right? The structure in this case is always a subject, verb, object. And how do you match a subject, verb, object in language with that represented in images? You also need to understand the concepts, right? In this case, the important concepts are plant and light bulb. You understand what a plant means, what it looks like in images, and likewise for light bulbs. And we know how to do concepts, right? All the part of local representations and line representations is all about understanding these concepts. But more importantly, you need inference, right? The verb that connects these two concepts that are surrounded. And when A surrounds B, that's very different from B surrounding A. So you need to understand what surrounding means, and that requires spatial knowledge. And finally, you need external knowledge because everything that I've said, it doesn't come automatically from data, it doesn't come automatically from large amounts from data, it comes from humans. And these four are perhaps the biggest sub-challenges in reasoning. And again, some other examples, right? You see all these amazing Clip, DALL-E image generation models. They take in a piece of text and try to generate an image. They work really well for an astronaut riding a horse, but you give it a horse riding an astronaut, it still fails spectacularly. And there's many debates surrounding reasoning, as I mentioned already. So some people think fully data-driven, bottom-up approaches can get us to reasoning. These have more data, bigger parameters. Some people think fully domain knowledge is the way forward, right? You need kind of symbolic knowledge, you need kind of define the knowledge graphs that allow you to solve your problem. And this whole spectrum can be seen as hybrid of neuro-symbolic methods. Combine the utility of data to learn different parts, like neural network portions of your model, and also combine it with domain knowledge. And that's the symbolic knowledge that comes in from domain knowledge. But even then along this spectrum, there's many, many design choices, right? Ideally, you want these methods to be differentiable so that you can make them compatible with gradient-based methods like deep learning. But sometimes you can't always make these differentiable. You also want to decide whether your concepts are discrete or continuous. The continuous is a more traditional case, using like dense neural network representations, but sometimes it can help to use discrete concepts. And finally, what's the best mix of knowledge and data? And again, this has many implications, right? Not just performance, but more importantly, how interpretable a model is. Models that are more good at reasoning, that have more symbolic knowledge, tend to be better understood by humans. How robust they are to both in distribution examples and out of distribution examples that we just saw, and fairness and efficiency and so on. So the main challenges we've seen, I showed a glimpse of these 4 challenges to motivate that problem, but going to more depth, the first challenge is about modeling the structure, right? What is the structure of the problem that enables us to take these individual elements and compose them? Simple cases, you can do a single step composition, like you just find one evidence and that leads you to the answer. That's called single step. And there can be many cases of multi-step reasoning, right? These are the cases that we're going to focus on today in the next couple of lectures. You can have temporal, where multiple data comes in different time steps. You want to compose for time steps. You can have hierarchical in the case of tree and graph structure. You can have interactive in the case of reinforcement learning. And if you don't know the structure, you can also try to do structure discovery, automatically learning the structure from data. The second biggest challenge is that of intermediate concepts. Can I parameterize my concepts to continuous states, like dense representations? Or could I use something like attention maps, which is still continuous but a bit more interpretable? Or could I go even more discrete? For example, so can I use words as an intermediate concept to help in reasoning? The third sub-challenge is that of inference paradigm. In the previous case, we saw you had a plant, you had a light bulb, the inference was surrounding a spatial relationship. So how can we actually calculate inference to compose this individual elements to more abstract representations? That can be representation-based in the case of your neural networks, but ideally you also want it to be perhaps logical, causal, spatial, all these things that you can inject into your problem to best compose individual elements. And finally, all of this is not possible without external knowledge, right? You need someone to design these models. You need someone with the knowledge of the problem. So typically, a lot of research is going into what's the best human knowledge or what's the best automatic form of knowledge to best inform reasoning. So again, 4 big sub-challenges. We're going to look at these over the next 3 lectures. Modeling the structure, which you compose your data. How should I parameterize intermediate concepts in intermediate levels? How should I compose different elements to inference paradigm, and what's the right form of external knowledge to inform my reasoning process? So the next 3 lectures, we're going to look at reasoning. Today, we're going to look at structure modeling, the temporal case and the hierarchical case. We're also going to look at intermediate concepts when they are continuous. So always going to stay in this continuous space, so either the case where we know the structure is given to us, it's going to make things a lot simpler. Next Tuesday, we're going to look at the case where it's more discrete. For example, if I have an interactive structure, take an action and get into the next state, that's a reinforcement learning paradigm. And if you don't know the structure, you might have to optimize over the structure. And optimizing over structures like trees and graphs is a discrete optimization problem. So we're going to use some reinforcement learning techniques to help us solve that. And also going to look at a case of discrete intermediate concepts like hard attention or using language as an intermediate concept to help you. And all of that, again, is discrete in nature. It's not directly compatible with neural networks, but there's ideas to allow us to solve these problems. And next Thursday, we're going to look at inference. We're going to look at causal inference, logical inference, and how that applies to reasoning in multimodal settings. And also going to look at external knowledge, like what kind of knowledge, especially common sense knowledge, from unstructured data outside of your problem is going to help you perform your task. And feel free to stop me if you have any questions, okay? So we've actually seen reasoning before. Just linking it back to the previous lectures. If the structure is single step, if the concept is dense and made of neural network representations, and if the inference is just based on combining representations, this is almost everything that we've seen previously, right? Representation fusion, either basic or complex fusion, alignment, all of this using like single step structure, using dense neural network concepts. All this forms reasoning. But the main idea for reasoning is to push beyond this single point. You want to go into multi-step structure. You want to go into a more interpretable concept. You also want to go to more complex forms of inference. Right? So the main goal of reasoning is to be more explicitly interpretable and robust beyond what we've seen so far. So firstly, let's go into structure modeling. The first type of structure that we're going to see very often is that of temporal. If you have data that comes in sequences like language, like videos, like high frequency sensors, how do I best reason over such temporal data? So in this temporal data, we're going to have multiple time steps. Each time step can have multiple modalities coming in because we're looking at multimodal problems. And perhaps you first like to do something simple. Just learn a representation, a local representation using ideas for multimodal fusion at each of these time steps. And then the biggest goal is to try to look at the connections and interactions across time steps, right? If what I said in the first time step relates to my facial expression, like 10 seconds later, or if one actor in the video corresponds to another actor in the video later on inside the video. So the biggest question is here is how can we capture these cross-modal interactions across time? And a lot of the methods that we're going to be looking at, I'm going to go into some details, but at a high level, it's all about memory. When we take in data coming at time steps, storing them into memory, and being able to retrieve them from memory at the right time when a new corresponding type of data comes in at subsequent time steps. And there's many ways of parameterizing multimodal memory. And again, if you have multimodal memory, you can try to find these connections, right? Something that is discovered subsequently later in time, you put it into memory, you try to link it with something that has been stored earlier in memory. That's how the connections and interactions are discovered. And many ways to parameterize this. RNNs, LSTMs are all examples of memory. Transformers can also be in some extension of memory, but sometimes people also try to be more explicit, like key value memory or episodic memory. So I'm going to go into details on the more explicit types of memory. So in all these memory mechanisms, opening this up, typically the big matrix. There's M locations and there's D dimensions. Each of these dimensions index which part of memory you're currently in. Each of these dimensions represent vector inputs that can be used to input into memory. And there's three big components, three big equations you want to look at in memory. The first one is taking in data at a particular time step and deciding what to store into memory. That's the input step. So typically the input step is basically a coordination function. If I have an input xt at a particular time step, I'm going to try to compare similarity with everything that I currently have in memory. That's empty, right? A similarity function. And you've seen many examples of similarity functions, right? All the work in representation coordination applies here, right? It can be cosine similarity, it can be correlation, it can be order hierarchical similarity, and so on. But if you look at a similar case, the simple case of cosine similarity, that basically amounts to taking inner product between each element in memory along the vector dimension with the input xt that's coming in. And then you probably normalize it. So this normalized vector, so this wt is basically a normalized vector of m entries. It tells you from a scale of 0 to 1, each of the m locations in memory, how much I should insert this new vector into memory. The weights over your m memory locations. And again, yeah, that's all representation coordination. Similar to attention models, transformers also do a variant of this, LSTMs also do a variant of this. And once you have these weights, the input matrix is essentially these weights outer product with your input xt, right? So taking xt, that's the vector of the dimensions that you want to put in. And over all these m weights, determining the weight of that vector. Right? Sometimes it can be all zeroed out. That means you're not putting it at that particular entry. Sometimes it's fully ones. I'm going to put that into the right memory location. So input is a m by d matrix. The next big step is writing into memory. Right? You have this input matrix, it's m by d. That's what you want to input into memory. How do I put it into memory while combining it with previous information inside your memory? So essentially, most methods do this from a weighted function. The new memory at time t sub plus 1, mt plus 1, is a function of your previous memory at the previous time step, mt, with some weight, 1 minus alpha, plus alpha times your input. Essentially a weighted function telling you how much I should weight my current input and how much I should negatively weight the previous information in memory. And again, this alpha t weight, there's many ways to learn it. It can be a fixed parameter. It can also be learnable, dynamically changing in every time step with alpha t instead of alpha. And all these recent parameterizations like LSTMs, RNNs, transformers, memory, they all make it learnable. I'm going to go into more detail about how to learn it afterwards. So together, this enables you to model these cross-modal interactions across time, right? You have some information in memory from previous time steps. You keep that with this exponentially decaying function, and we get new information that is similar based on your coordination function, right? That determines your W. You can then enter that into your memory. And the last example, the last equation is our reading, right? At the final time step, you accumulated your memory across all your time steps. Reading from memory is basically a summary function, right? Taking a vector beta t. Again, this beta t is a vector of m dimensions across the number of dimensions of your memory, and using that to perform a weighted average across all memory locations. And again, this beta t can be a fixed parameter, or typically it's learnable. It's going to depend. Well, in this case, it's not depending because you only have it at one time step. But if you want to read it multiple times from memory, it can also depend on the current time step. So some extensions. The first extension is about more on the input level, right? The input is all about finding similarity. If I have an input vector xt, I'm going to compare it with all memory locations I currently have using a coordination function, and then decide which most similar entry in memory I should use that as input. And this is all good if different time steps provide different information, or you see corresponding or repeating information very rarely. So I see like 1, 2, 3 time steps. I see different information. It goes into slots 1, 2, 3 in memory. At 4, I see something similar with 1. I coordinate with 1. That's all good. You're still kind of, there's not too much overlap. But in many cases, you might see repeating information, right? You want to keep getting information that wants to coordinate with current entries in your memory. So the problem with this is that if you start applying this on cases with a lot of repeating and redundant similar information, they're slowly going to start rewriting your memory again and again and again. So there's some extensions. I think the biggest extension is to not just address by similarity, by coordination, but yeah, sorry about that. So again, the biggest next paradigm of input is not just addressing by similarity, but also addressing by location, right? You want to keep track of all the input places that you've read in so far. So that's your WT matrices from previous time steps. And when you get a new WT at a new time step, I'm going to apply a function that takes into account all the weights that I've done either at a previous time step or more into the past. And usually people apply the rotation function, right? If I have seen slots 1, 2, 3 in the future, and I get something similar that may overlap within slots 1, 2, and 3 in memory, I'm going to put a location 4, right? So this ideally will lead to a contiguous block of similar representations in memory that you can then apply. You can then extract so that you don't overwrite your memory in previous locations. Right. So again, taking an xt, computing a similarity that gives you WT, the proposed set of weights across a memory location at t time step, applying something like a rotation function or any function that takes into account previous weights, and using that to weight your inputs. Another extension people have proposed is that in writing, people have found that typically you have many more time steps than you have memory locations. You don't want your memory to be as big as number of time steps. Otherwise, you can just store everything. You don't need these fancy memory methods. So one thing people have found that if you can also propose smart ways of erasing things from memory, then you have better opportunities to store more information in memory when that information comes. So how can I dynamically determine both erase and write functions? We've seen just write, but also erase. So erase can be very simple. Again, it's just based on ignorable parameters. Your empty, your memory at time t step is perhaps multiplied by a function 1 minus alpha t. Alpha tells you how much to erase, and erase is against a learnable vector from 0 to 1. So erase being fully zeros, meaning it erases the complete entry in that memory. Erase being something at 0.5 would erase half the information from that memory. And once you've done erasing, you can then input stuff into your memory using the same equation. The third big innovation is more into this exponential moving average. This is perhaps the biggest equation in memory. Right? You want to keep track of previous memory information, MT at previous time steps, and weight them such that you can also combine it with new information coming in. So in this case, the exponential moving average. Basically, the further along you are in the past, it exponentially decays the amount of information those memory inputs are going to contribute. And it's a very important function. People use this in time series all the time. Essentially, the goal is to smooth out any short-term fluctuations. And so you can capture these long-term trends. Right? If you have a big peak at this current time step, it's not going to capture the entire peak. It's just going to smooth it out by still accounting for previous information you've seen previously. And people have also tried to integrate these exponential moving average functions into transformers. I think you see like the first one is the standard transformer architecture. The second figure, the most important part is this EMA layer, where you're taking the input at a particular time, and you're going to apply exponential moving average with respect to previous input. So even applying this before you do all your self-attention in your transformer layer, these folks show that it helped a lot. All right, so this moving average has also seen applications in others, like transformers, other sequence models beyond memory itself. Another interesting thing is that everything that we've seen seems to be recurrent. Right? In order to compute these memory mechanisms, you have to take the current input and store the previous input, and then you have to recurse at the next time step and so on. And this may not seem easily parallelizable. And that's a big reason why, when transformers came out, which is based on convolutions and recurrences, people ditched LSTMs and typically started using transformers. But I want to make a side note, which is that a lot of people are also still working on these LSTMs and trying to make them more parallelizable. And the key idea is that many of these recurrent formulations have equivalent formulations in convolution space. And especially this exponential moving average, right? Everything that you've seen, the exponential moving average is a recurrent function, right? It takes in the previous time step and does a moving average at the current time step and repeats at the next time steps. And this might seem recurrent, but you can actually implement this as a convolution. And the key idea is that this exponential moving average function is equivalent to just computing a final memory at the final time step through a convolution of all the inputs across all time steps stacked together with a convolution with this convolutional kernel K. Right? So you can actually compute this in parallel by stacking in all your inputs across all time steps and just doing a convolution with one matrix, which is parallel. But the big issue is that this K is going to be huge. Right? This K will actually be the size of the entire sequence. It's going to be order T. And that's not good. That's basically saying that if I have LSTM, instead of recursing over T dimensions, T time steps, I'm going to do a convolution with a matrix as big as this T time steps. But fortunately, a lot of people are still working on this. There's been a lot of approximations, optimizations. These two are very good references. They've been building upon these convolutional models or LSTMs to really get it to scale to very, very, very long sequences. So check these out if you're interested. And I want to highlight that actually some of these methods, like for example, Lou's paper, efficiently model long sequences with state spaces, they scale to even longer state spaces than transformers, even though they don't use transformer architectures. So all of those was more optimization in the unimodal space. I haven't really talked about multimodal for a time. But again, all these ideas are applicable. So some folks have kind of extended these memory mechanisms to the multimodal space. So when we started, we assumed early fusion, right? We looked at all these time steps with modalities coming in at every time step, and we assumed that we will learn a representation at the beginning before inputting into memory. So that can be seen as early fusion, or as you might have called it, fusion at the very raw level. But there's many other ways to parameterize your memory to take into account different types of fusion, different types of representation, right? It can be the fully fused case, which is what you've seen. Every entry in memory is a fully fused representation. You can also think of every element in memory as being a coordinated representation. You can also think of every element in memory as being a factorized representation. There's been a little bit of work done here and there. I'm going to highlight some of them, but again, many, many interesting design decisions to explore, combining the ideas of multimodal with the ideas in memory. So going deeper into some examples, this is an example called extending long short-term memory for multi-view learning. So this paper, what they did was to take in all these elements at individual time steps and first maintain separate representations. I'm not going to fuse them right at the beginning. So when I maintain these separate representations, I'm going to have a memory sequence for the first modality in red, and a memory sequence for the second modality in blue. And then the main question is then, how can I fuse these multimodal representations in memory across time, right? How do I learn these functions? Right? If they're just straight arrows, that means the memories are completely independent. You do like a late fusion, you encode both things in memory, you do a combination at the end. But if I start interchanging information at every time step, you're going to get a blend of both early fusion and late fusion. So how these folks do it is that they basically interchange information with two parameters, right? Whatever my memory for the red modality, that's going to be a function of the memory of the same red modality plus a weighted input from the red modality and a weighted input from the blue modality. So the parameters alpha and beta basically determine how much of the same modality information at each time step goes into memory versus information from the other modality going into memory, the interchanging of information. And likewise, I can do something parallel for the other modality, right? The blue memory at t+1 is a function of itself, and alpha plus input for blue and beta plus input for red. And with different settings for alpha and beta, you get different parameterizations of multimodal memory. So if alpha is 1, beta is 0, that basically means that I'm only interjecting memory information from the same modality. That's a fully unimodal, or fully unimodal in memory, but late fusion perhaps at the end after you've encoded everything. If beta is fully 1, that means I'm also fully interjecting information from the other modality. That's a fully fusion case. So what you have storing into memory is a fully fused representation. And with alpha and beta, both numbers between 0 and 1, you get some hybrid. You get both a fusion hybrid and a factorized fission hybrid. Because you're combining information, but you're also keeping information separate. Yes.
What is
I see this as fully fusion because when alpha is when beta is fully 1, that means whatever I'm storing into the red modality's memory is going to be something as a function of the red modality and also completely the blue modality. The blue modality is completely coming in. So that's why I think this shows the colors, right? You just look at the fully unimodal case. Your current input is yellow. The same modality is going to be red. You get something called. For the fully fusion case, your current input is yellow, but the other modality's memory is blue. You get something green. And when alpha is 1 and beta is both 1, you're taking in the current modality, you're taking in both memories from the same modality and the other modality, you get something like brown. But different parameterizations of how you can combine information from the current memory cell and the other modality's memory cell. Okay, so you see this type of, not doing early fusion, but keeping memory cells separate across the modalities at the beginning and interchanging within memory space. And you also seen the case when alpha and beta were predetermined, right? Alpha was 1, beta was 1 or 1/3 each. You can also dynamically change these alpha and beta for them to be 10 across time. So I'm only changing the alpha to alpha t and beta to beta t. And again, these alpha t and beta t can be dynamic. They can be learned through self-attention function, from similarity functions, and so on. And this paper back in 2018 found that this improved upon the dynamic version, the static version. So dynamically determine alpha and beta at every time step outperforms the statically initializing alpha and beta as hyperparameters. Okay, so that was memory and representation, right? Combining representation, fusion, fission, and so on. One interesting thing is that I don't think anyone, to the best of my knowledge, I don't think anyone has combined it with coordinated representations. So that could be an interesting direction to explore. The next thing I'm going to do is memory plus aligned representation. We look at fusion, representation, but also alignment. And the motivating example here is that if you want to navigate a robot in this house, the house, whatever state you're currently seeing the observation, as the robot moves around, the instruction is head a bit ahead and pull out the double doors on the left towards the kitchen and stop upon reaching a counter. So all these robots are good. You can train them using imitation learning, reinforcement learning. Go into more details about training these interactive robots next lecture. But one question you probably want to ask is, can the robot keep track of where the robot has visited previously? You don't want a robot to keep moving around in a circle. Right? So one very simple idea is to equip this robot with a memory bank, right? Taking either representations or states or representation of the states of all the locations that have visited previously while trying to navigate towards the correct location. So you can then, if you have a memory bank, you can then apply a transformer or any contextualized representation that takes into account the current state that you're seeing, all the states you visited previously, and the instruction that you want to accomplish through these states. So that's where the contextual representation comes in, and use that to predict your next representation or your next action. And once you've done that, you can try to store, again, the new representation back into memory and recurse. And again, all the ideas of contextualized representation can apply to how you parameterize these transformers. You see a lot in the last lecture. And again, all the ideas of memory mechanisms can also apply to how you structure the memory. I think these folks that did some initial experiments, the memory was basically all the states previously. So there's probably a lot more that can be done in this space. But yeah, all the ideas in contextualized representations and all the ideas in memory can also apply here. So what are the biggest use cases of memory? We've seen a lot of methods, but perhaps the most compelling use case are tasks involving repeating the input in some specific way. So these folks who introduced neuro-Turing machines, a form of memory, back in 2014, had a couple of experiments. One experiment was direct copy. I give you a sequence of numbers into your sequence model, and I ask the sequence model to repeat back those numbers to me, and the sequence model do that. And you can clearly see that if you have memory that you can store every single number and retrieve it from memory, that's going to help a lot. But some of you might already try this like LSD and transformers they're not really good at this. Repeat copy, I give you a sequence of numbers, 5, 1, 8, 6, 7, and I give you a number of times I want to repeat those numbers. You have to repeat those multiple times, right? So this requires even more memory than just directly copying. Associative recall, so if I give you a sequence of numbers, and I give you one number, you want to find the number after it. And so if you give 8, you should give 6, because 6 is after 8. If I give you 1, you should give 8. If I give you 6, you give 7. And this sequence of new inputs comes in afterwards. So again, you have to memorize the initial sequence of numbers so that whenever a query comes in, you can output the next number as the queries come in. And sorting. I don't know why, but some people want neural networks to be able to do sorting. And again, that requires storing into memory and outputting from memory. It's much harder if you don't have these memory methods. And these folks showed it, right? These neural Turing machines, which is a very early example of memory, perform much better than just your classic LSTMs. Another very, very big use case is that of very, very long range sequences. So recently, again, this is a paper on long sequences with structured state spaces, but also these new benchmarks have come out for very, very long sequence modeling. There's no equivalent for multimodal just yet, so a lot of open work there. But some of the examples of long range sequences are list operations over very long sequences of numbers, like computing the mean, max, and sum. Very long document classification and retrieval, image classification via sequence of pixels. So I take an image, they'll do convolution, I take every pixel, power up, and try to classify the digit in the image or the object in the image. Pathfinder, which is a very nice example. So given these two examples, there's 2 dots, right? You see a white dot here, you see a white dot here. It's positive if the 2 white dots are connected by a path. And the negative if they're not connected by a path. So it's actually pretty hard for humans even. You need to trace all the pixels within the image. And also generating long speech signals, right? So all these methods are shown to work really well in these cases. And I also play some of these audio clips from generating from these methods that generate very long audio sequences. Yeah, I don't know much about music, but sounds good to me. Another very interesting application is cases where information changes across time. Nowadays, people train all these big language models on static data from the internet. So all the language models that you see nowadays were probably trained on internet backlogs from at least a year or more than a year ago. What if information changes? Right? The mayor of Chicago changes, or the head coach or soccer team that's going to change across time. You can't really adapt your language models very quickly to all this changing information. But a good thing about memory, and especially these retrieval augmented or memory augmented language models, is that you can look into memory, you can look what information is there, you can change the information as you desire. So some examples, I'm not going to go into details, but some examples of language models equipped with these memory mechanisms that allow them to be updatable in their information. Cool. So that was the first part of the lecture. The key takeaways are that we looked at temporal sequences, cases where multiple steps across time, multimodal data coming in. How do you best model these cross-modal interactions across time when these can be potentially very far away? And the key models we looked at is that of memory models that take in inputs, weighted by the inputs, that keep track of these memories across time. It seems recurrent, but it can be able to make parallelizable. And how do you read out from memory when you want to? And we saw the basic case in a unimodal case, a lot of language sequence modeling. You can also combine it with representation in multimodal learning and also alignment, right? Representation, we saw cases of instead of doing a refusion of these elements at every time step, but keeping separate memory tracks and fusing them or factorizing them at the memory level. For alignment, we saw how we can kind of keep track of these memory mechanisms and do contextualized representation learning above these memory and also your new inputs. And the use cases are more useful for storing or copying information, long-range interactions, and cases where we want to control the internal information inside these models. But still, a lot of open challenges, right? A lot of what I talked about is in the unimodal case. There's not that much work in multimodal long-range sequences. And perhaps benchmarks are our first way. Like, what are the big good benchmarks that actually require interactions over a long range? And so you might have seen that many multimodal benchmarks nowadays, if you look at one particular frame or one particular word in the question, you can start already associating them. It's not that temporal, or doesn't require long-range interactions. So how can you build very good benchmarks actually require interactions over a long range? One interesting thing is that there's always this debate. Should I use fully neural network, fully black box trained models from big amounts of data, or should I spend time designing all these memory mechanisms? And people have found that to some extent, if you train these big language models, they can still serve as memory. They can still serve to retrieve information. You can take these language models, and you can ask a question like Dante was born in something, and the language model would retrieve and still output to some extent correct factual information. So one thing a lot of people are working on is benchmarking the extent to these pre-trained models are able to capture memory, memorize and enable retrieval. And to what extent do we actually need explicit memory mechanisms? There's a lot more. I don't know if LP has mentioned it, but on the alternate semester, he teaches advanced topics in multimodal course. And one of the big challenges we talked about was memory and long-term interactions. A bunch of papers, some of them I've touched upon today, and a bunch of open questions. And also the synopsis, which is the summary of group discussions in that class. Cool. But any questions so far on memory, sequential modeling, temporal modeling? No? Good. So the next type of structure we'll look at is hierarchical. When we think of hierarchical, perhaps the first thing you think about is that in language, right? In language, you have these sentences. It seems like a sequence, but there's some underlying hierarchical structure in the forms of syntax trees. So this very nice paper, as a motivating example, this very nice paper tries to do image text retrieval. So the image over here, I have the text, skis of a man in a red jacket. How do I match these two? So one thing you can do is you can start by parsing your caption into a syntactic structure. Basically looks like a tree. And you can start matching. You can also detect all the objects inside the image. You can detect the man, the skis, and so on. And then you can start matching these up in the form of this structure. So first, for skis, can I coordinate with all the images of skis, with all the object regions of skis inside the image? So that's again a coordination function. Everything that you see in the coordinated representations apply here. Can I do it for man? You can detect all the man in the image. And skis of man will basically take the intersection, or the object region with skis and also object region with man. And likewise, can I do it for a jacket and red and jacket? So you can again take these intersections, and finally that gives you a very principal way, a very nice way to actually retrieve to determine whether the image and text match. Right. So all of these compose well. The probabilities flow upwards. They match, and if any part of the image or the text doesn't match at every part of the tree, you can basically stop and say that this is not a matching image and caption. So these models are very nice for a couple of reasons, right? Perhaps the best reason is that if I look at this model, I'm happy. It's not a big pre-trained model. I don't know what's going on. I know exactly at every step of the model what's going on. I can debug it if necessary. I can see, is it a problem with detecting speed that the model has done? Is it a model of composing these relations that the model has done? I can debug the model very easily. Right, so that's, again, a big advantage of reasoning is that I can design models that I understand and also models that I can very easily control. But again, this is hard. Right? It requires you to parse the question. It requires you to select objects. You need to hand design this tree. You implement this from scratch. You can't just download a model from Hugging Face. And again, one of the biggest challenges is how can you actually design a model that operates on these trees? Right? We've seen LSTMs, we've seen memory methods, they operate over sequences, but not really yet models that apply on these trees and these arbitrary structures. So that's the extension, right? We have these linear chain models, transformers, or linear chain models. How do you apply them to arbitrary tree models? And the biggest question here is that you have these connecting nodes that perhaps take in many children, and you have to recurse over multiple levels in a tree. And perhaps more generally, it's a good time to talk about graph networks, right? Trees are basically a special case of graphs. In any case, you have many examples of data where graph is a modality, like social networks, economic networks, internet, and so on. So the next part of the talk of the lecture, we're going to be going to graph networks. Essentially, the biggest application in graph networks is supervised learning. So if I have a graph with leaf topology, these nodes connected to other nodes, and I learn representations either for a node in the graph or learn representations for the entire graph itself, so that I can make a classification. The node level is, for example, if I have a social network and some people are connected to other people in the social network, can I use these nodes and edges to determine if someone is a human or a bot? There's a node level classification. I'm going to do a graph level classification. If one particular structure or protein, as former graph is a protein, another structure is another protein, and so on. And I can also do unsupervised learning, right? So again, unsupervised learning also is at the level of either nodes or entire graphs. In this case, nodes, can I embed these nodes into representation space where similar elements or similar representations in the representation space correspond to nodes with the same topological structure that are connected to similar nodes. So all of these methods, all these applications, the biggest core methods are graph neural networks, right? And these graph neural networks basically start with a graph tree, which can be seen as V, a set of vertices or nodes in a graph, A, an adjacency matrix, which is binary, whether an edge is connected with some other edge in the graph. Typically, we also have X, some input features. So these input features can be seen as the node of images, a graph of images, or the image features coming in. There's a graph, like a tree of sentences or words. You have all the word embeddings coming in at every node. And Y is your prediction task, and that can be either supervised or unsupervised. So the key idea in all these graph networks is that you want to take into account the structure, how these nodes are related to other nodes. And that key idea is exactly that you want to generate these embeddings of your nodes based on the embeddings of nodes that it's connected to. So if I want to look at the embedding for node A, this should basically be a function of the embeddings of all the nodes that A is connected to. So in this case, B, C, and D. So I'm going to take in all these embeddings of B, C, and D, combine it into a function, and use that to predict the embedding for node A. And I'm going to recurse, right? Because I don't know the embedding for B. The embedding for B again depends on A, because B is connected to A. It's also going to depend on C. And likewise, C is going to depend on A, B, E, and F. So you have this very nice recursive function where every node is dependent on the embeddings of the nodes that it's connected to. And one same thing is that you see A here and there. So it's kind of recursive, right? So it calls for a function that basically has multiple time steps where you keep an embedding for A at a particular time step and use that to infer embeddings of other nodes and A itself. And then that becomes a new embedding for A, and then you can start repeating. And once you repeat enough times, you see all the connections in a graph, you get a best embedding for A. So every node here, basically, you're going to repeat this for all the nodes. Every node defines a computation graph by looking at the children of those nodes, the nodes that it connects to, and recurses. So if you do that, you get embeddings for all your nodes, and then you can look at multiple layers, as you mentioned. You can start with an embedding for all your nodes. You can use that to infer the embedding of a node that's connected to, and the next layer will then infer the next embedding of a node that are connected to, and so on. So secondly, you're going to update the embeddings, all these nodes that repeat. So this function is perhaps the most important, right? How you see the structure of the problem, how you kind of combine them based on the nodes they're connected to, but how exactly do we combine them? And that is known as aggregation or neighborhood aggregation. There's multiple ways. You can basically do an average. You can take the embeddings of all the nodes you're connected to and just take a sum or an average of these embeddings. Some normalization here. And again, K in this equation is the number of layers or number of repetitions, right? So you have a node embedding for V at a K step. That's going to be a function of all the embeddings for other nodes U that's not equal to V at the K minus 1 step they've computed previously. And also the embedding for V at the K minus 1 step, the previous embedding for that node at a previous step. And that essentially gives you the embedding of that node at a new K step. You can use that to overwrite the embedding you've inferred so far. You can do average pooling, you can do convolutional pooling, that means you graph convolutional networks. You can also do attention pooling. So that gives you something very similar to self-attention models, but self-attention transformers are on a single chain. this basically extends them to graphs where you have arbitrary connections between one node and all the other nodes. And finally, once you've done this, you've done all this training, all this embedding, you can get embeddings for all of these nodes, and then you can define your objective function. So in this case, we're showing the objective function for an embedding ZA. So that's the node embedding for ZA. And Y is perhaps your label. You're doing node level classification. That's your label for this node A. And in this case, it's binary, so you can just define a binary cross entropy loss to train your embedding for ZA. And again, this, when you train ZA, it's going to be a function of all the other nodes, right? Because the final embedding for ZA is dependent on all the other nodes. So that's node level, but you can see very easily how you can extend it to graph level, right? If you have embeddings for all the nodes in a graph, you can then do a final pooling. Like what we said, like reading out from memory, you can do a final readout from all the nodes in a graph and get a final embedding for the entire graph and train it with respect to some objective. Any questions so far? Cool. Some experiments. So we've seen this already. If you have these kind of tree structured grammar in your languages, you can do image text retrieval much easier if you account for the structure. And it's a lot more work, right? There's a whole line of work showing that if you inject syntactic structure of language for NLP tasks, you can help language sentiment analysis, semantic matching between different parts of text, question answering, language modeling, and also makes it more interpretable. You can interpret the attention scores. So this one is actually a tree transform, integrating tree structures into self-attention instead of a full self-attention over all elements in all words in your sequence. You just look at the attention between words that are related in your tree. So that makes your attention scores much more interpretable. I'm going to go into a bit on this paper. And this is a very nice paper, I think, because this paper essentially gives us an intuition for why graph neural networks work. And the key idea here is called algorithmic alignment. I'm going to look at my problem and what are the steps of reasoning required to solve the problem. And I'm going to try to relate it to the steps of reasoning that are capable, that are achievable by a particular neural network. So there's 4 classes of problems, right? One class of problem is called summary statistics. If I have a bunch of elements, I pick out a summary across all these elements. That can be seen as a single step reasoning. For example, what is the maximum value difference across all these treasures that I have? Another class of problems is called relational argmax. For example, what are the colors of the fully paired objects? That requires you to define a graph over all objects and do a single step inference, right? Look at the furthest pair and look at the colors. There's a class of problems called dynamic programming. For example, what is the cost to determine a monster by looking at by following the optimal path to that monster? So that requires you to solve the optimal path problem. And finally, you have NP-hard problems. And basically what this paper did was to look at a couple of class of methods. One is MLP. So you have the input, MLP, output, easy. Deep sets, which is a method designed for sets. So you have a collection of items that are unordered. For example, if I have a set of numbers, I want to find the sum of these numbers. These numbers are unordered, right? It shouldn't be sensitive to the order of these numbers. So what I can do is I can take an MLP to encode each number as a first MLP, each number as in a set. And then I can take a sum, right? Because sum is an order invariant operation. So that basically means your network is no longer invariant to the order of your input. And then take another MLP to produce the output. It's a very nice neural network based on sets. And finally, you have your graph neural network. So, okay, that can be layers. We start with your source node, and the k embedding for the source node is a function of the k plus k minus 1 embedding for that node, and also a k minus 1 embedding for all the other nodes connected to that source. And finally, you see the embedding for all the nodes in the final iteration. I'm going to take a sum and take a prediction over them. So that's going to give you an embedding for the entire graph. And what they found was that each of these problems align very well based on the structure of the problem with one particular class of method. The summary statistics, it's a set-based problem, right? If I want to take a sum or the maximum value among a set of numbers, it should be order invariant, and deep sets most aligns with this type of problems. If I have relational argmax, that requires me to do one-step reasoning over a fully connected graph over all these objects. A one-layer GNN aligns the best. If I need to do dynamic programming, if I want to find the shortest path from a source to all the other nodes in the graph, that requires me to iterate multiple times, right? That requires a k-layer GNN. And obviously, if you have an NP-hard problem, none of the neural network methods align best with it, because if you can design one, you're going to win every award in existence. And the key idea here is that many multimodal reasoning problems graph like it, especially those that require complicated reasoning. If you have intuitive physics, or if I throw a block at the other block, what's going to happen? If I have visual question answering requiring very complex questions that requires to relate across multiple objects, or if I have shortest path questions in multimodal reasoning. We're going to see some shortest path next week on reinforcement learning, where you have to kind of, as an agent, go to like a next object or the closest object and so on. And one key idea here is that graph neural networks, especially k-layer graph neural networks with multiple layers, they actually tackle dynamic programming really well. So recall, one classic example of dynamic programming is shortest path, right? This is the Bellman-Ford algorithm. You're going to initialize. Let's say you have a source node S, and you have all the nodes from U as U. On the first iteration, you initialize the distance from itself to all of these nodes being some infinity cost. And every time you visit a node, I'm going to update the shortest path from that node to yourself using this function, right? The distance from the neighboring nodes to yourself, whatever the smallest that is, plus the distance from that neighboring node to that new node. You can basically recurse, and once you recurse enough times and you see all the nodes in the graph, you're going to essentially get the all node shortest path solved, right? The shortest path from yourself to all nodes in a graph. And graph neural networks actually mimic these Bellman-Ford algorithms really well, right? So in graph neural networks, you see something like for k, to the number of GNN iterations, the GNN layers, and for every node in the graph neural network, I'm going to recurse by taking the embedding for that node as a function of the embedding for the nodes next to it at the previous time step, as well as the embedding for that node at the previous time step. And that actually mimics this Bellman-Ford algorithm. And the only thing that you're going to learn is to mimic this equation with your MLP. And people know that with MLP, you can approximate any function, right? So it should be able to kind of mimic this minimization and the distance function that is useful in Bellman-Ford. But the issue is that if you have an MLP doesn't have all these things, right? It doesn't have GNN iterations. It doesn't iterate over all nodes in a symmetric way. It doesn't have this aggregation that respects the structure of the node with all other nodes. It's just one MLP. So for MLP to learn this, you must learn the for loops, all layers of for loops, and also learn the recursive function in the inside. And that makes it very difficult. And you can look at this paper for like a more precise formalism of what it means to be difficult. And they show this, right, on two very nice tasks. One task is Sudoku. So we've all played Sudoku, right? That requires you to fill in a number, look at all the numbers next to it, whether it fulfills the rules. If it doesn't, you have to delete it and backtrack across possibly multiple time steps. And also relational VQA. So people started with clever. Given an image, what is the size of the ground sphere? That's one step reasoning. Relational questions. Are there any rubber things that have the same size as the yellow cylinder? That requires you to form a fully connected graph and look at everything that's yellow and look at the same yellow size. That's a two-step reasoning. And also, people started extending clever to sort of clever to pretty clever. And these are more and more challenging data sets. And for pretty clever, the type of questions are which object is closest or k steps away. So that's exactly the type of problems that require you to solve like dynamic programming like Bellman-Ford to find all the distances from a particular object. And exactly. So you look at a number of training samples you need and the test accuracy, NLPs perform really badly. Deep sets a bit better, but still pretty bad. And the more layers of GNN that you need, that you have, the better it performs at the same number of training samples. And ideally, you want as many layers of GNN in this case as the number of objects. Because if you have that many layers, you can solve shortest path to all the objects within your scene. Cool. So key takeaways. We've looked at we looked at graph neural networks. We also looked at this very nice analysis paper that AC looked at these 4 levels of problems. Some are just perception based, you can do one step. Some require multiple relations across multiple steps, like dynamic programming. And they basically show that some methods are more suitable to single steps. Some methods like K-layer graph neural networks are more suitable to multiple steps. But there's still some open challenges. All of the work, again, has been in the unimodal case, where the elements are in the same modality. So it's easy to define the relations, easy to define distance functions. They're on the same representation space. And how to handle cross-modal interactions in these relational problems is a big challenge. And that perhaps requires us to design heterogeneous graph neural nets, right? Graph neural nets that apply on node embeddings that are not from the same modality, like from one social network, but from different modalities, right? Requiring images as some nodes, text, social networks, users as all these nodes. I think there are formal connections to be made between cross-modal interactions and relations. All these relations, they essentially cross-modal interactions between elements in this problem, right? So how can I formalize these connections? And perhaps then you can look at different taxonomies of cross-modal interactions, those requiring like one step, or those requiring you to solve using dynamic programming. And finally, one interesting thing is that many data sets claim to require reasoning, but people have soon realized, oh, they don't require reasoning, so I'm going to build a more difficult data set. We saw this with this thing, right? You started with Clever. People claim that Clever was data set for reasoning, and people realized they can solve it using one step of reasoning. So people built sort of clever, and then people built like pretty clever, so to get more and more difficult reasoning data sets. So how can we actually quantify the reasoning that is required to solve a data set versus just one step perception? That's a big challenge. Cool. So to summarize, reasoning is all about compositionality, right? And in order to compose your elements in the right way, you typically need to know the structure of the problem. And we've seen examples of structure in the continuous case, or where the structure is given in the case of temporal or hierarchical. You can use memory methods in the case of temporal structure. You can use tree-based methods in the case of tree structure, like syntax. You can also define graph neural networks in the case of graphical structure. Cool. Any questions so far? All right. Move on to concepts. We want to go more into structure next lecture in the case of discrete structure or optimizing over discrete structures. But we're just going to look at concepts. So in concepts, we've seen many cases of continuous concepts. In fact, many that we've seen so far with graph neural networks, with memory methods, all the concepts, all the intermediate representations were continuous. And that's good. But sometimes you can also start to explore different ways of parameterizing these concepts. You can use attention maps. You can use even discrete concepts. And again, the more discrete, the more interpretable you are. So there's been a lot of push for concepts that are mix of both symbolic and also compatible with neural networks. So we're going to look at some examples of concepts based on attention. So let's say you have a problem called this like question answering problem. Is there a red shape above a circle? You can start by trying to solve this problem by parsing it, right? You can parse the question. You know that you first should attend to all the red parts in the image. And again, you can basically take the word red, you can take the image, and you can train a neural network to detect all red parts of the image. You can do that using your CNNs or transformers and so on. And ideally, what you get is a heat map, an attention heat map over all positions in the image, where it's higher if it's red and less if it's not red, right? So you see these like 3 highlighted regions because those are the 3 red parts of the image. You can then attend to the circles. Again, an attention heat map over all the circles in the image. And then you can attend to things above a circle, right? So that basically takes the attention map for everything that's a circle and shifts them one cell upwards. So now you have everything that is red, everything that is above a circle. You can then combine it, right? And combination is basically taking all the attention values and taking the max or taking the intersection. And again, this gives you a very nice, very principled way of doing this whole problem, right? You know at every step what is correct, what is incorrect. If you find that this heat map is screwed up, then you can train a better heat map for detecting circles. If you realize that any like a reattention or combination is screwed up, you can check it as a bug in your code. that reattends by shifting above or combines by intersecting these heat maps. And there's a lot of recent push for these type of methods. These are all called neuro-symbolic methods that combine the power of neural networks because you're using CNNs or transformers to obtain these heat maps. So that's all good. You can detect these objects really well. But at the same time, you're using something symbolic. You're basically taking a question, parsing it into a sequence of operations, and combining these sequence of operations in the right way to get the answer. So again, recall structure, right? This is again an example of a hierarchical structure that leverages the syntax and language. And people have slowly started to design more sophisticated methods. They have more difficult questions, including the ones that are clever, that require reasoning. You can first take a CNN, like a mass RCNN, detect all the objects in the image. And for each of them, summarize its size, its shape, its material, its color, its X, Y, Z coordinates, because those are important towards answering the question. And if I have a question like how many cubes that are behind the cylinder are large, you can first parse the question into a sequence of steps, right? You first need to detect everything that's a cylinder. You need to look at everything that's behind the cylinder. You need to look at which are cubes and which are large, and then take the intersection, right? And each of these steps can be completed by just filtering in this database, right? You know which are the cylinders, you can get it. You know which are the X, Y, Z coordinates, you can look at what's behind the cylinder object. You can look at which are cubes based on the shape. You can look at which are large, and then you can take the intersection and count the number of entries. And these are all good. Like you can see immediately the pros, right? It's robust. Either it works or it doesn't. If it doesn't work, you can look at, oh, did I mess up detecting cylinder? Did I mess up detecting my position? Did I mess up parsing the program? Know exactly where it doesn't work. It's typically more data efficient because you're using so much prior knowledge, and it's super interpretable. But you can also start seeing its big cons, right? This is very engineer. It's very specialized. If I take this and introduce a new shape like a star, I'm gonna redo a lot of things. If I'm gonna apply this to like a real world scene instead of this synthetic scene, you're going to redo many things. And sometimes it's not fully differentiable. So in this case, you're gonna get this program with multiple steps. These steps are discrete steps, right? It's very, very difficult to make them differentiable. So how you actually optimize your final answer with respect to everything in a fully differentiable way is very difficult. And there's gonna be more in the next lecture on how do you approximate this. And again, like we all want to do large scale pre-training, leverage the large amounts of data. How can you make this compatible with large scale pre-training? That's a big challenge. So to summarize, and again, I'm gonna, like some of these cons are just by design, it's by your philosophy. Some of these cons can be solved. We're gonna look at more discrete cases, discrete optimization next Tuesday. But to summarize, look at reasoning. And reasoning is all about combining knowledge. You have all these local representations that you have aligned representations, so much knowledge you've gained about multimodal data. How do I best combine it in the right way to solve a problem? And again, reasoning is difficult because of compositional generalization. Things that you see with respect to some set of elements and their compositions doesn't necessarily generalize to the same concept with different compositions. If you want to train your data on this, you probably need exponential amount of data. You need to see all the compositions in the world. And that's not feasible, right? So a lot of methods still fail. And we've seen 4 big challenges: knowing the structure, the way things are combined. This is the subject verb object that can be much more complex cases. Temporal and hierarchical tree and graph structure. We've seen some examples of concepts that are fully dense, and also based on attention maps, we're going to see more based on discrete concepts. We're going to see more on inference. For example, surrounding is an inference. How you should combine both concepts. This is spatial relation. We're going to see causal, logical, spatial relation. And finally, all this knowledge that we need either from humans or from domain knowledge. Cool. To summarize, today we looked at temporal structure. And we looked at memory and temporal networks to account for temporal structure. For hierarchical structure, we looked at tree and graph networks. And for intermediate concepts, we looked at continuous case, either dense concepts or based on attention maps. And next, we're going to go into so in this case, it's all structure is either given or is learned in a differentiable manner. It's all continuous. That's all easy. Next Tuesday, we're going to look at interaction and discovery and go into discrete optimization. And next Thursday, we're going to look at causal and logical inference and external knowledge. Cool. That's all, folks. Any questions? How do I understand a word neuro-symbolic? I think it's both neuro and symbolic, right? You want to inject symbolic knowledge. And I personally think the right way of injecting symbolic knowledge is making it compatible with gradient-based methods, right? So you inject some of these attention maps, for example, that you've seen so far. You're using a symbolic fact that there's certain words that you can use to query your image to get attention maps, but still differentiable. Right? Attention maps can be obtained using CNNs or transformers. And once you're done with that, you can then compose all these symbolic knowledge into your final answer. And ideally, the composition function is also something that's differentiable. Right? We looked at cases where it's hierarchical. You can build graph networks. Next week, there's some you can go from discrete to continuous through approximations. It's not always perfect, but sometimes you can do it and you can get something differentiable. Yeah, but it's a big debate, I think. If you're on Twitter, people are debating this every day. Deep learning and symbolic methods. Yeah. Any other questions? Oh, I guess I forgot at 11:10 you all were supposed to fill in the highlights form. So I guess do that now if you haven't.